Hi everyone. So welcome to this video, supplementary video. So this supplementary video discusses the topic of scaling analysis within boundary layers. So we have been in class discussing the derivation of boundary layer equations using order of magnitude analysis. We have also derived a solution over flat plate using the Blassius solution, which involves the similarity transform. But those are typically more mathematically involved, and you have to solve differential equations. There is also a more shorter approach where rather than seeking an exact solution, we will try to seek solutions where we can at least suggest the parameter dependence of different forces and stresses and so on. And we kind of did this while doing order of magnitude analysis, but I thought it would be good to do this separately. So in this video, essentially what we will discuss is how does boundary layer thickness scales, and then we'll discuss the shear stress scaling rather than deriving. So we did derive shear stress in Blassius solution, but how can we derive that using a scaling analysis? And then we'll go into the topic of developing flow and fully developed flow. And finally, we'll end with boundary layer separation. So this will be like a short video, but the idea here is rather than going through an exact solution, we will go to a more scaling analysis or order of magnitude analysis approach. Right. So just to quickly refresh your memory, we have been discussing this in lectures that let's imagine we have a solid surface where X denotes the direction parallel to the surface and Y denotes the direction perpendicular to the surface. Uh, and we have been saying that there will be a boundary layer in the regime of high Reynolds number where there will be some gradients within the boundary layer for the flow, right? So recall that while deriving the order of magnitude analysis, we had essentially suggested that Reynolds number, that the boundary layer thickness scales as 1 by square root of Reynolds number, where Reynolds number was defined as rho UL by mu, where L was the length of the plate. Okay, where L was the length of the plate. So this was the definition of how we started, defining the boundary layer, and we said the higher the Reynolds number, the lower is the boundary layer thickness, which makes sense because the more Reynolds number I get, the thinner boundary layer I'll get, and the region where the gradients are present will be smaller. So this was the approach we took. But then we also noted that this assumes that the length is L. What if we say the length is X? Or because we know that the boundary layer actually changes with X. So to this, to clarify this, what I will do is, for the purpose of this video, I'll write delta of L, which means that the delta, assuming that the distance is length is L, that's a boundary layer at thickness at distance L from the beginning of the plate. But we can also have delta of X, which is basically this. This is denoted as delta subscript X. This will basically become where we'll just replace everything will replace by L by X, and we'll get this, or you can write this as mu by ux. Okay? So this is what you get. Or finally, you can imagine we can also write delta of x mu x by u. Okay, so it is a square root of square root dependence, and it increases distance with the square root of x. And imagine, and just recall that this is for the assumption the velocity is u outside. Okay. So let's just quickly check the dimensions because we have not discussed this in detail yet till now. This is meter square per second, mu, right? Mu is meter square per second, x is meters, and u is meter per second. So you can verify that delta of x will get the units of meters. Okay, it's always good to get a sense of dimensions. And nu is the kinematic diffusivity, or momentum diffusivity, and has units of meter square per second. Okay? So this is something we have discussed briefly in class of how the boundary layer thickness scales with x, and it goes with square root of x. So we can imagine the boundary layer thickness will go with distance x. All right. So the first thing, this is the first thing we did. So let's the second step was to get delta of x. The third step we want to do is calculate tau naught. And again, let's do not forget tau naught. Tau naught is the wall shear stress. Wall shear stress in the system. and how can we get this value. So recall that we had done this in class, that this would be equal to, in exact form, this will be equal to del Vx by del y plus del Vy by del x. And we could simply ignore this term based on order of magnitude analysis, or by scaling wise, you can think of this as mu u delta of x. Okay, so I can basically say at each location x, my velocity in the y direct, sorry, in the x direction is changing with u. The scale is u, so Vx has the scale of u, right? And delta y has a scale of delta of x, right? And this is what you get. Now we can substitute delta of x from the top result here. So if you substitute this here, right, this is what you will get. So you'll get tau naught scales as mu u cube rho, mu u cube rho by x. So dimensionally, this is how this scales. So you can verify, you can substitute this delta as mu x by rho, or mu x by rho u, right? And when you substitute this is what you will get. All right, so this is something we have not derived in class. So can we actually verify whether this result is actually correct? So we didn't really put dimensions here. So you can verify this by writing actually tau naught by rho u square by 2, right? And will not carry around the factor of half. So that's just, pre-factor, but this is something we did find an exact solution for. So this becomes square root of mu u cube by rho by x by rho u square by 2, right? Or in the, if I'll just remove the half factor, because that's something we are not interested in. We'll just say rho u square, and we'll say this is mu u cube rho by x, okay, rho square u4, because I'm just taking everything inside the square root. Or if you see this actually becomes uh, tau naught by rho u square, tau naught by rho u square becomes mu by rho ux, or you can write this as mu by ux, which is dimensionless. And if you recall, in the class we had derived the prefactor here, and the prefactor is actually something about 0.664 or something like that, which is very close to 1. So rather than doing the analysis, this also gives us a very correct parametric dependence, and this allows us to calculate, some scales in the system. So this is the third thing we calculated. So let's just recap what we have done. Boundary layer thickness at a distance L, boundary layer thickness at a distance X. We verified some dimensions. Then we found the wall shear stress, and then we found that the scalings actually match with the Blashes solution. And finally, let's also calculate the force or the drag force in the flat plate case. So note that I'll come back to a more complicated geometry. In the flat plate case, the drag is completely only the shear stress drag. We are not talking about a form drag, which is the pressure drag, only the shear stress drag. And in this case, this will be tau naught. Okay, and what should be the tau naught? We should take the tau naught at not some general x, because our tau naught has x dependence. Now we're trying to calculate a global property, right? So we'll basically take tau naught as a function of when x is equal to L, right? So in our scaling analysis, we'll replace x as L, right? So we'll write this as replace x as L and have width L W into L. Okay. So if you do that, we get this result. So let's do that. Mu u cube rho, mu u cube rho by L times W times L. Okay. And we get this as mu u cube rho L times W. This is the drag force scaling. Again, we did not describe this exact result in scales in class, but we did derive the non-dimensional version, which is the drag coefficient. And again, I'm not taking care of the two factors, the rho u square by 2, just, we'll just look interested in the scales. This will be a rho u square times WL. So you take the area parallel to the surface, and we have mu u cube rho L times W by rho u square times L times W. This gets cancelled. And what you will get essentially is again mu u cube rho L by rho square u4 L square. And you can verify this. This will get simply rho ul by mu, or mu by rho ul here, or this becomes Reynolds number to the power minus half. Okay, so this is how the drag coefficient goes. And in the class we had seen that, just clearly write minus half. In the class we had seen that this actually becomes 1.328 times this factor, but again, we're able to get pretty accurate results just through scaling analysis for drag force, okay? So I really want to make sure that you are able to follow the scaling analysis and, try this on problems, not just flat plate problems. Wherever you see any boundary layer analysis, always try to use this approach to get a sense of what kind of parametric dependence you will get. Because sometimes, you don't have, uh, there are not enough techniques to solve the entire problem, but at least you can get a sense of parametric dependence in your system. And boundary layers, like I mentioned in class, are very prevalent. You will see them likely in your research problems in various fields, right? So this is scaling analysis inside boundary layer. We calculated the boundary layer thickness, then the shear stress, and then the drag force, and we saw how these results are very related to the Blashes solution, and we are able to reproduce all the parametric dependence. All right. So the second part of this video is about the entrance length, uh, which we have not discussed in class at all. And I want to make sure we are able to cover this slightly more detailed, in slightly bigger, longer detail, is this idea of what happens in internal boundary layers. Internal boundary layers. Okay. So we have discussed boundary layers, but we were only discussing that in kind of reference to drag force. But we should not forget that you can have a system where, like a cylindrical pipe or a parallel plate, where you can imagine that the boundary layers will start to, look something like this. There will be a boundary layer here. Let's call this Z, or let's call this X just to keep it things simple. This is X and this is R, and you have delta of X, right? So you have boundary layer growing in the entrance region, and then the boundary layers will start to meet at some point. And the portion after which they meet is basically called the entrance length, LV, or entrance length. Okay. And after the entrance length, the flow becomes fully developed. So the flow is fully developed beyond this entrance length. Flow is fully developed beyond this entrance length. So we had used this in part 2 of the course, where we kept kind of referring to this fully developed assumption. But what does that mean? It actually has implicitly this idea of boundary layers coming together and meeting them. So essentially we're saying when we find velocity profiles in fully developed region, that velocity profile is separate. That's after these boundary layers have come together and interacted or sort of touched each other at this length LV. So can we predict this entrance length is the question. So if you think about it geometrically, this is very similar to a flat plate system, right? Where the radial direction becomes a y direction and x direction is simply the x direction here. So you can use all the scaling analysis we were doing even just today in this video, and you can use that to predict this length LV. Okay, so let's try to do that now. So how to predict this length LV? So we know that we want, basically, when will this length become clear, or when will this length be the entrance length, is when the boundary layer thickness becomes equal to the radius. So let's call this as R. And what we are saying is we want to find the value of length LV. So delta by LV. So I'm using the formula which you derived here. Okay. So this is the formula here. So I'm saying delta is at LV should be R, right? Should be R by LV. Let's just keep things a bit simpler right now. Let's just say L delta by X is nu by ux, right? So when X is LV, then delta is R. Okay, so that's what we are saying. And when if you put the value, we get uh, R by LV becomes nu U by LV. Okay. So we want to basically get the value of LV, that's the goal. So what we'll do, square the result. So let's square the result. And what we get is R square by LV square is equal to nu by ULV. Okay. And so one of the LVs get cancelled, or we get LV by R becomes equal to UR by nu, or something like rho UR by mu. Okay. LV by R. And in the pipe flow, we define Reynolds number based on the radius. So note the difference here, and this is just the choice. You can choose to define Reynolds number based on the actual length also. We were defining length, we were defining Reynolds number based on the length in the x direction, but here we are defining based on the radius, and both are perfectly okay. You can define based on diameter. The main point is that LV by R is somewhat basically related with RE, where RE is actually more precisely defined as rho U D by mu, or 2 rho U R by mu. This is a standard definition in a cylindrical pipe. Is Reynolds number is defined based on the diameter, and that's because it's just convenient. That's the right length scale, and so on. But this is what we get from the analysis, and what basically this is telling us is the larger the Reynolds number, the longer it will take the system to become fully developed, right? And that's an important result, because if you're at really large numbers, you have to wait a distance before you can claim that the system is fully developed. But what is the exact result? So the exact result is actually given in the book. I think it's in chapter 7, but the exact result is LV by R is actually equal to 1.18 plus 0.11 RE. Okay. So, but for large Reynolds number, which is the limit we are studying, because we have assumed large Reynolds number, this will typically basically go away, and you'll get 0.11 RE, which is what we get from our scaling analysis. And again, our scaling analysis was done assuming large Reynolds number, because you were assuming potential flow outside and so on. So we were able to get the scaling analysis correct, right? So this is flow inside internal boundary layers. So whenever you have channel flows or systems flowing inside, you have these boundary layers coming up. When they meet, the system flow becomes fully developed, and we can predict their entrance length by simply saying that the boundary layer thickness will reach the radius of the pipe or the channel. Okay, so this is also a cool result, and you can see how scaling analysis is pretty powerful here. The third thing we want to discuss is the flow around these drag around objects. So always classify any flow type into these two parts. One is this flow where predominantly in one direction, which is the flow like a channel flow, or something in between two plates, or when you have flow around the object, which is typically bidirectional. So I want to basically emphasize the difference here. The difference is that in this case, if you think about this, the drag force will most predominantly be the shear stress, because the skin drag is basically in the x direction, right? And the pressure is normal, so it's in the radial direction. The pressure force really won't contribute to the drag force, which is in the direction of flow. So the flow is happening something like this, which is in the x direction. So it'll be skin drag only. But when you have flow around the objects, as we has discussed in the class, we can have this, we can have this feature of the boundary layer separation, where you can start to see sort of these vortexes coming around on the trailing side of the cylinder, and the drag can be both FD form plus FD skin. And it is very important to understand the distinction between these two. So this comes from pressure, okay, and this comes from the shear stress. And the important thing to understand is that this form drag or the pressure drag happens when you have, the separation, like it becomes more and more dominating when it's a separation, because pressure drop scales as, this is something you can remember from your calculations for the potential flow. Pressure scales as the inertia, rho u square, right? So the pressure drag, FD form, will scale as rho u square, but will also need this factor of perpendicular area perpendicular. And the idea being that the larger the projection area, because pressure can only act in the perpendicular direction. So if there is no perpendicular area, let's say the body is streamlined, like some sort of, let's imagine there is some solid like this, streamlined body. So here A perpendicular would be much smaller than comparison to, let's say, so let's color this. This is a streamlined body. And this is like a bluff body. So this is a bluff body which has a very large A perpendicular. Okay, so bluff body. So the more the body has a bluff-like feature, which has a larger A perpendicular, then the drag force from the form drag starts to become dominant. Whereas the skin drag is actually dependent on the A parallel. That skin drag is mu u delta A parallel. Okay. And this mu u delta is the same as what we derived in the previous portion, which is the scaling analysis. So if we were to basically take the ratio of these FD skin by FD form, you get mu u by delta by rho u square and A parallel by A perpendicular, and this becomes mu by rho u delta, right? A parallel by A perpendicular, and don't forget that delta is itself rho u L delta by L. So this is Reynolds number to the power of -1, and this is Reynolds number to the power -12, or this will become total Reynolds number -12, A parallel by A perpendicular. And this is a very important result, because this shows that the skin drag actually becomes less important for large Reynolds number, right? If I keep on increasing the Reynolds number, skin drag becomes less dominant. So, and the form drag starts to kind of, really become more important. So that's why another factor that I can control is this feature of A parallel by A perpendicular. So to basically reduce the form drag, which is something we don't want, right? We want to reduce the drag as much as possible. You want to have a streamlined shape, and that's what dictates the entire science of aerodynamics. When you want to design planes, when you want to design automobiles, when you want to design any of the water transportation like ships and so on, you want to understand the sort of drag because of water or air, and you want to keep this system as streamlined as possible. Because when you streamline it, you are reducing the form drag, and this portion of the form drag would basically reduce. Okay, so this can also be very clearly seen from the scaling analysis. So yeah, so I mean, in this portion we discussed 3 portions. First, we discussed the flat plate, boundary layer thickness, shear stress, and the drag force, the skin drag force. Then we went into the entrance length and derived this entrance length result within internal boundary layers. And finally, we discussed this drag around objects and how form and skin drags can compete with each other. So I hope this video was useful, and I look forward to seeing you in the next video.